All right, so thanks for coming out. You half who made it. It is it.
I think we should have like a bonus.
Well, here's the thing. I'm going to say you guys will be in on something now. It's up to you if you want to tell the rest of the class or not, or it can be a funny joke. So I won't be here on Monday. I won't be here on Monday or Wednesday. I'm going to pre-record the lecture that I was going to give, so you can watch it on your own time. Up to you if you want to tell the people who are missing whether or not class is canceled Monday and Wednesday. So, if they're listening to the video, they'll know that, but it's up to you if you want to get them to listen to the video or not. So officially, no class Monday, no class Wednesday. I will post the video that you would have had in lecture with me, so you can just watch that sometime before I get back. So it'll be about a 45, 50-minute video about gas laws. Good? And they are also missing out because we are going to make three-dimensional Vesper structures using marshmallows.
I knew that you guys had recorded it this morning.
So what I'm going to do is I'm going to work us through this slide and then the next slide, this one, lone pairs, and then the rest of the class will just kind of work on it as a group and kind of make models. Oh.
What about the 4 electrons?
Did I? That was tetrahedral. Did we do that one?
Yeah.
Yeah, that was that one.
Okay.
All right. Because this class definitely got through 4. Then my 1 o'clock got through 5 and 6. I'm just trying to catch everybody up. All right, so that's your Mountain Day surprise. Happy early Mountain Day. I mean, I'm going to be in Cancun, so it's not like I am missing out on a lot of Berry College. I will be hanging out with the coolest electrochemists out there. I mean, if they're all cool like me, then it's going to be a huge party, right? Turns out they're not, so they're very nice people.
They're not. Wait, so they're not like you because they're really nice? I'm confused on where your point is.
Yeah, a little bit of both. Yeah, I am maybe not as nice as they are. I hope they watch them. If you're watching this, I love you guys all. They're great. I know they're not. They're at much fancier colleges. All right, so let's say because last time we left off, it is really hot in here. Is it hot? Or I'm just wearing a sweater. All right, so we left off with the tetrahedral where we moved into three-dimensional space, right? And now our carbon and our hydrogens are 109.5 degrees apart. The two last ones we need to look at are trigonal bipyramidal and octahedral. So when we're looking at trigonal bipyramidal, we're going to put our phosphorus in the center. And then I need to put 5 chlorines around it. So I've gone from putting 4 chlorines, or 4 hydrogens to 5. So this will still have 0 lone pairs, but now 5 bonding groups. So 5 electron groups altogether. All right, so this is where we move from regular shapes to kind of crazier shapes. So the easiest way to think about this shape is we're going to put 1 directly above the phosphorus and 1 directly below the phosphorus. So the phosphorus is your torso, right? You got 1 chlorine on your head and 1 on your feet. And you're going to put the other 3 around your center like in a hula hoop. So 1 is a little bit farther forward, 1 is going backwards, and 1 is in the same plane. So we look at the angles this makes. All right, this chlorine to this chlorine is 180. All right, so if I had a circle, how many degrees are around the whole circle? 360. Now I have 3 things in my circle. How many degrees apart would they have to be? 360 divided by 3. 120. So now the chlorines that are around the center are 20 degrees apart. And then this chlorine to any one chlorine in the center is now 90 degrees apart. Good, good, good. All right, let's go ahead and do 6. So 6 is going to look very similar to 5. Where I have a sulfur in the center, now I have 1 fluorine up, 1 fluorine down, but now I need to put 4 molecules around the center. All right, so now my center has 4 things sitting around it. So this angle is still 180, and this angle is still 90. But now I have 4 things around my hula hoop, so how many degrees apart would all 4 of those things be? 90. All right, any questions on those 6 shapes? Linear, triangle, trigonal, planar, tetrahedral? Okay. All right. This is in your textbook. This is just, it's going to be a handy reference for what we're going to do for the rest of the class. So put those off to the side. All right, so we just looked at all molecules that had 0 lone pairs. So what effect will lone pairs have on the shape of the molecule? So if we don't distinguish between lone pairs and bonding groups, we say they're all the same, whatever they are, they're all the same to each other. Then the electronic geometry, right, where the electrons are. Is the 3-dimensional shape. So everything we just said, all 6 of those shapes were electronic geometries. And that lone pairs and bonding groups all counted the same. And so when you're looking at this table that's in your book, you'll see there's 2 different columns. There's this one called electron geometry, and there's this new one called molecular geometry. Molecular geometry includes lone pairs and means that lone pairs act differently than bonds. And this is going to be the big thing, lone pairs. So a lone pair is going to take up more space than a bond. And it's going to force the bonds to be closer together than they would normally like to be. The lone pair needs so much space. Let's see what my example is. All right, so we'll do an example together. We'll do water, and then I'll kind of let you loose on the rest of these so you can use your little sheet to try and help you out. So let's do water. All right, there is my water. And if I was counting things, how many lone pairs does the oxygen have on it? All right, 2 lone pairs. All right, how many bonds does it have stuck to it? 2. 2 bonding groups. So altogether, we would say it has 4 electron groups. So if it was just regular 4 electron groups, what shape would you call that? It would be regular tetrahedral, right? We would think it looks something like this. It's not very good tetrahedral, something like that, right? But these lone pairs need a lot more space than they get in this. So in this shape, I'm not giving the lone pairs enough space. They are going to spread out even more and force these two hydrogens in the water to come closer to each other. So in reality, right, if this was tetrahedral, this would be 109.5. But in actuality, that bond distance is, let's see what shape is that. I think it is 100 degrees. All right, so smaller angle, the H's are closer together. And so if you have 4 electron groups, 2 of which are lone pairs, this shape is now called bent. Which you can see on your little worksheet or handout. You have 4 electron groups, 2 of which are bonds, 2 of which are lone pairs. You would think it'd be tetrahedral, but because you have 2 lone pairs, it's now called bent. And those H's are closer together than you would expect. So, what I'm going to have you do is sit with whoever you want. It can either be your study groups or just whoever's in your row. And all of these examples just about are on this handout. So do the same kind of thing. Draw the Lewis dot structure, build it with your marshmallows, and see how it fits in 3-dimensional space, and then write down the correct name for it, and I'll walk around. All right, so the pink ones are the central atom. These little white ones are going to be the things that are stuck to it. So.
You're on the board. This is brother dog, Anthony. How'd you play? They go.
That's what I do on my tracks. Put like my finger right
When you are.
I'm selling it in these ages.
Here are your loan pairs. Here's loan pairs for whatever
Wait, is that what we're supposed to be doing?
That's not terrible. Yeah, so across the top it is total groups
So you just want us to like put each one of these together? Just this?
Yep, and then just kind of keep track of what the new name is.
What's the first one?
Okay, so.
Back here.
One of these pictures.
All right, here's the picture. All right.
Two of them look great.
So, it's going to be, yep, here's up here. And then that one here. Yeah, here. Yeah, so I've got, this one.
No, don't use those. I can't see that one. All right, this is 5 total electrons, 4 bonding.
That's trying to
Three will bond through middle, but now it's 6. Like when I put
That makes sense.
just use these as they have marshmallows on.
We cannot say we want those 4 years.
Yeah, that.
Oh, it's right there.
All right, we made all the ones. Okay, here now.
Yep.
Yeah. Gosh. Yeah, we didn't say funny. I'm really. Okay, come back.
You do know you're just still recording, right?
Yeah.
It's just recording the conversation, it's kind of weird for anyone watching.
Are they all going down?
You can sound conversation, like thinking about the trainees building.
All right, I'll do it.
You're missing class.
We don't get this one-on-one, we lose.
Can you just like get regular things for like 20 minutes?
I got it. I can share it and think like, yeah. Right. I'm gonna be like, this is very important.
And then you write.
All right.
Quick question on these. How does the
Right, so would be, so if we had done more like
I was never.
right here. That's a lone pair and that's a lone pair. So what it means is you had these 2 chlorines, right? If it was all 5 atoms, 2 chlorines, they're gone now and they're 2 lone pairs. And so it was 120 and now it's 90.
We don't have enough of it. Yeah, no. Oh, how many? I can't see it. Like a little steady totally worth it.
A lot of hobbies like seesaw.
What molecule?
They could have been on the boat and left, but they got the boat. I hate them.
I'm super impressed.
I got kind of bad after that. I was like, I don't even want to watch them more. And I seem like a Mexican dude. What he said, when he thought he was going to get out, but he said he got to stay. So I seen the car with a little pipe. Both pipes. Like when he first got in there, and after they were good, and the big pipe was there. The police really killed It's been a while since
All right, we're doing good here. Yeah, so it's easy if you start off every time. Maybe it's just the same thing. Call, so you can have 5 responders. you start off with a free run center, one of the and then
I know what you're talking about.
you take another one
And this one would go right. You know all the ladies. Here's mine. Here's mine. How do you?
I think with your picture, like what are those all 5 stories?
Got excited by the side. Hey, that is a good word.
All right, has everyone made it through just about all of these? 2 or 3 more minutes.
Wait, how many are we supposed to do, like, the 5 and 6 ones?
Yeah, you
Are you gonna go?
can. I am going
See through it?
Are we able to eat them like that?
Yeah, can we just?
No, they want it back.
Yeah, now I don't want them down.
It's all stretched out.
I don't know stats. I gave a lot extra than the other ones.
Yeah, sounds good. I have to eat.
Yeah, you have to eat some of the other ones. They have a hole in them. They may not make it to my food. Yeah.
You should present that to the
All right, so in our last few minutes, I'll work through the naming of these. All right, so if I had NH3 with that lone pair hanging off of it, right, if we counted them all the same, then they would be tetrahedral. But this lone pair is bigger than expected. And so it's going to force all of these hydrogens to be closer in space than what we would think. And so these angles are closer to 100 than they would be in 109. So it's easiest for me to think about, like, what family do they belong in, right? 4 electron groups, okay? Automatically, tetrahedral would be 4 electron groups, but 1 is a lone pair. So it would be 109, but now 1's a lone pair, so it has to be less than that, so like 100-ish. And it gets a name trigonal pyramidal. And, right. Because it looks like that. It makes a triangle shape with 4 faces. Triangles. I don't know. Looks like pyramid. All right, if we have SF4, we put all of the electrons around fluorine at once. You would come up too short. like you haven't used all the electrons altogether, you could have 34 and you're only using 32. So the last two have to go on sulfur. So this has 5 bonding groups, one of which is a lone pair. And so if it had been a regular molecule, it would be 180 top to bottom and then 120 around the center. But now these two are closer in space than they would normally, so that 120 goes down to, like 110 or so, and it looks more like that. We'll do this and this. We'll say those are going back and behind. So more like a seesaw, where these two are on the same plane and those two are on the same plane, and the lone pairs are going straight up. All right, so now we're going to take SF4 and remove one more fluorine from it. So now it would be R. So we had, wherever that went, right, it was originally trigonal bipyramidal, but now I've taken away 2 of the fluorines that were attached to the different atoms, and now these angles are less than 90. Right, because now I have a lone pair on the top and a lone pair on the bottom, and I was at 120 around the center, but now the 120s are closer to 90 to each other. So that gets a T-shape. All right, we could take away one more fluorine. And make a linear, but I guess I don't have that in my notes. You can take one more away. That'll be linear. We'll do 6 electron groups. All right, so this was octahedral. Originally, you had a sulfur in the middle and 6 fluorines around it, 6 bonding groups. And now we have only 5 bonds. And now 1 lone pair. So again, this was, oh, I'm missing one. Yeah, sorry. Let me draw that better. Did I mess up everybody's drawing? All right, so originally that was an F, and it was 90 degrees around the center, and 1 up and 1 down. Now there's a lone pair. So this is going to force these fluorines to be farther up than we thought. And so this was 90 degrees, and now it's going to be less than 90. And this gets the shape of a square pyramidal. So before we had triangle bottoms and the trigonal pyramidal. This is a square bottoms pyramid. So now it's a square pyramidal. All right, we can take the same molecule, and now we're going to take one more lone pair off of it. And the optimum geometry for this is just a square. So again, the angle between these have gone back to 90 because it's being squished down as much from the top as is being squished up from the bottom. So now these angles are 90, and these are back to 90. So that one's called square planar. So, on my things for you to do this week, as we're moving on, your lab on Monday is to, I have like one more thing to talk about today. Sorry, that was misleading. Your lab on next week is to fill in a gigantic table of all of this information, which you can now do ahead of time, which means that if the more you do before you get there, the less time you have to spend in lab. Because it's going to be like PCL5, draw the Lewis dot structure, draw it in 3 dimensions, how many bonding pairs, how many lone pairs, what do you call it, something, something, something. So you can do most of it before you get there, and then it'll save you time when you are there. All right, so in summary, all of that stuff is determined by number of electron groups, which really depends on the correct Lewis structure. And then, depending on our geometry, it's either going to be molecular or electronic, or molecular includes the lone pairs, and electronic doesn't include the lone pairs. They count them all the same. All right, so the last topic in Chapter 10 is polarity. And there's the other piece of information you have to have for lab next week, polarity. All right, so let's say you have a Lewis dot structure. When I defined a covalent bond, I said the electrons are shared evenly across a covalent bond, but that is not exactly true. As usual, not exactly true. It's actually more to it than that. So if I have this molecule here, HF, right, drawing it like that, I have made how many covalent bonds? 1, right? I made 1 covalent bond. And that 1 covalent bond, in theory, has the electrons evenly shared back and forth. But what do we know about the electronegativity of fluorine? Really high, really low? Really high. So does it want electrons or wants to give them away? It wants electrons, so it's not going to share evenly with hydrogen. That's not possible. All right, so from electronegativity, we know that F is very electronegative, which means the fluorine wants the electrons. So this bond is not going to be evenly shared. In reality, the fluorine's going to be a little bit negative, and the hydrogen's going to be a little bit positive. And so we show that so if I had a triangle in math, what would that tell you to do? Like in words or in math, like if I had a big triangle, like this. Right, change in, right? Or I mean subtract. So that is the big letter delta in the Greek. It means big change. Little delta means little change. And so this is a little bit negative, and this is a little bit positive. So those deltas tell you, I guess, how much change. So the fluorine's a little bit more negative than you would expect, and the hydrogen's a little more positive than what you would expect. I have now made 2 poles, right? Just like a magnet. I have a positive end and a negative end. So I'm going to call this now a polar bond. Which means there is a end of it that's a little more negative, and there's an end of it that's a little more positive. What if I look at this molecule, H2? Is there any difference in their electronegativities? No. So is there going to be any poles to it? No. So this is a nonpolar molecule. Nonpolar bond, which makes a nonpolar molecule. Polar bond, which makes a polar molecule. So if we look at a few more examples. Let's see what else do I have left. Yeah. If you have more than one atom, right, or more than two atoms, right, so we had HF and HH. If you have 3 or 4 atoms, having a single polar bond is not as obvious if it's directly polar or nonpolar. And it's going to depend on its Vesper shape. So if we draw CO2, and we draw H2O, all right, here's carbon dioxide with 2 bonding groups, none of which are lone pairs. Its shape is linear. All right, and this shape is now bent. So if I have a linear molecule, is there an electronegativity difference between carbon and oxygen? Like a little one, right? A little bit. They're kind of next to each other. So I'm going to indicate the direction of the electrons. So which one's more electronegative, oxygen or carbon? Oxygen. So which way should the electrons go? To the oxygen or away from the oxygen? To. So I'm going to show it using these fancy arrows, where the arrow shows the direction of the electrons and the plus sign is where they are coming from, right? So a little plus, a little minus. All right, so thinking way back to your physics, recently or not recently. If this is linear, and they're pulling in opposite directions, is there a net change? And so this is polar or nonpolar? This is going to be a nonpolar molecule. All right, because even though each bond is polar, they're pulling in opposite directions. So overall, it's not polar. All right, let's look at this guy as our last thing. All right, so we have this, and we have that, right? They're pulling evenly, but do they cancel each other out? No, right? Because now they're making kind of a peak. So this would be a polar molecule. All right, so on the video recording, which will be up hopefully